Well, it won't screw you up. I mean, it's not like it's going to be putting more stuff in your head that'll move other stuff out. All right, so there's that. Yay. Okay, so what I want to look at, and this might actually have occurred to some of you guys, if you guys have kids yourself, is the results of my son Max's 2-year checkup. Now, he just turned 5 1/2, which is great, because now he's huge. But I have the results from his 2-year checkup, and I love the discussion that happened. Actually, I probably should turn the lights down now for this. Yeah, a little bit sharper. So, here are the results from his checkup. This is what my wife brought home. I wasn't able to go to his checkup, so she brought this home. He was in the 80th percentile for weight. He was in the 90th for length, and my favorite, head girth. 85th percentile, they measured around his head, which I just love. And I asked my wife, did they knock his hair down before they did that? But, so, now here's some subscripts that we like to use in class, just because we hate writing 80th percentile all the time. So, a P sub 80 just means 80th percentile. P sub 90, 90th. P sub 85, 85th. Okay. How many of you have either taken your kid to the doctor to see this, or you've dealt with percentiles some other place? See, some of you have, couple hands. Not many hands. Anybody going for nursing? You got some nursing students? So you guys will deal with this with the, what's that exam? TEAS, thank you. The TEAS exam, yes, that's the one. That one, assuming you were in a certain percentile, you get a check mark in a box that says, yes, they satisfied this. So that's what I kind of want to get in today is I want to start by talking about what a percentile is. So those of you guys that have played with percentiles before, what do you remember about them? If anything, it might be that I don't remember anything about them. Like I learned them at some point, they've gone away. But at the same time, I want to chit-chat about them today. Go ahead, Jordan.
Isn't like 80th percentile considered like kind of a way of standard deviation, where it's like that much away from the actual average or the middle?
Love it. Love it. Jordan, this is a fantastic point. I want to mute the screen. Actually, I'll just slide it over here. I love what you just did. You've given us the perfect segue, actually, to why we even care about this. What Jordan just talked about was the measure of variation, which was, and he used the word actual, I think, right? The actual distance from the mean. I think I heard that. Maybe I wanted to hear that. Sure. But he went like this. He put the mean here, and then he put his hand out here to indicate the distance from a data point. So in other words, we're comparing all of the data points to a fixed value that is the average, right? A fixed value. So what I kind of like to loop measures of center. That's an S. Measures of center and spread, or variability. And this is kind of, like I said, the stuff that's going to be on your, oh, there's Kristen. Just go ahead and drop it up here at the front, my friend, thank you. So you got measures of center and spread. Those I kind of call, I like to loosely refer to these as absolute position. Absolute position. And that's why when you took your hands and went like this, Jordan, that's an absolute position from average. It's a distance that can be measured. You know, if this is an 18 and this is a 22, that's 4. And if this is an 18 and this is at 14, that's -4, which absolute would be +4. And so I like to call these, and this is me, this might not be universal, I like to call it that. What we're about to start talking about today, just to compare and contrast that, is what this is, which is relative position. And we'll come back to this and why it's called this momentarily. But Jordan, what you just said is great. You said, is it somehow tied into standard deviation? It's another way of measuring. Besides, it actually isn't tied directly to standard deviation, but it's another way of quantifying things in some different way. So yes and no. No, it's not tied directly to it, but yes, it is another quality way of discussing it. Awesome, awesome. Other ideas about percentiles. What do you got? What do you got? If you've heard them before. And maybe you've totally forgotten what they were. What do you guys think? Any ideas?
Well, I obviously had it wrong, because for the longest time I thought it was, there was only, like for example, 20 or 80th percentile, I thought that there was only 20% who did better than you.
That's exactly what it means. That's essentially exactly what a percentile is, though you don't have it wrong at all. Check this out. Check this out. Did you hear what David said? He said, when I see 80th percentile, he thought that meant 20% did better. Now in this case, it's not so much better, it's just bigger, heavier. But that's exactly what a percentile is. Now, if in case this is kind of like, wait a minute, that doesn't make any sense at all. What I did was, I drew a sample, which is, don't write this down please, I'll have this posted for you guys later. So, here's 100 baby weights, randomly sampled. I say baby, 2-year-old. White, American, male, 2-year-olds. That's pound weights of a random sample of these 2-year-olds. Okay, boom, there you go, you got it right there. Now, that's also nausea-inducing to look at. It's like, oh my god, 100 numbers. So let's put them into a histogram form. Could you guys find the average of that, if I asked you to? Could you guys find the average of that? How would you find the average baby weight of this? That's the median baby weight, careful. We can find the median baby weight, right? By chopping. So chop the lowest, chop the highest, chop the lowest, chop the next highest, next lowest, next highest.
We should actually sample these guys.
So using technology,
Yeah.
let's talk about this. Just again, to tie into an exam review. If I gave you this data right here and said, find me the average, find me the standard deviation, find me the median, find me the mode of all this data, how would you do it? How would you set up your TI to do this?
L1 and L2.
Why L1 and L2, Jordan? Love it.
It's a 2-bar stat.
It's 1-bar stat.
1-bar stat with 2.
Good, because what I've given you, it's a little bit trivial, because a lot of times when you have 1-bar stat, L1 and L2, you actually have ranges of values down here. But what would you put in L1 to calculate this average?
The 20.
That all the way across. That would be L1. What would be in L2?
Frequency.
Number of boys.
You got it, Mimi. Right, how many 20s? So 3, 1, 2, 2, and so forth. And then you'd run 1-bar stats, L1, comma, L2, and out would come. If you don't put the L1, L2, and you just run 1-bar stats, it'll happily give you an answer. The wrong one. It'll give you the wrong answer. It'll give you the wrong median, the wrong everything. Cool? Cool so far? Where's the mode? Where's the mode? That would give you the mean and the median and the standard deviation. Where's the mode? Mode is 30. The mode is 30 pounds. And many students ask me, why doesn't the TI give you the mode? Well, because it doesn't. I mean, I don't know a good answer for that. But as far as finding it, it's the easiest one to find. Look at the graph, highest bar, that's where your mode is. That's where your mode.
Have
Cool?
we ever used 2-bar stat?
No, because, well, yes in 244, but I don't like 2-bar stats on the TI. We do it in Excel instead. It's when you're actually comparing 2 data sets to see if there's correlations or relationships between them. So if for example, comparing the Max's baby weights, or not just Max's, but 2-year-old baby weights to what they ended up being when they were 3,
Oh, okay.
that would be a 2-bar stats, weights at 2 and weights at 3. Here, there's just one data set, the weights in pounds. That's just the one data set. Yeah, we definitely use them. We also like 3 and 4 and 5 and 6-bar stats.
Right.
But for this class, we just stick with one. Just looking at the one set of data.
But TI also uses median.
It does. It just doesn't give you the mode. Right. And so you don't have to do the chopping because the TI will take care of it for you. Okay. How would you describe this data? Got some skew? Got some skew? Yeah. Anybody call it bell-shaped? I wouldn't disagree with that. We could measure the skew. Again, this is one of those things. You can look at that. Some folks will look at that and call it skewed. It's slightly skewed for sure. It's definitely not perfect. It definitely doesn't have a 0 skew. But you've got it. You see, that's the thing. It's kind of bell. You can use that PSSC to quantify how skewed it is. But all I'm looking for is you guys looking at that and calling it whatever you want to call it. Call it skewed. Call it slightly skewed. Call it bell-shaped. I'm down with that as long as whatever you do based on that is correct. So if you call it bell-shaped and act as if it were bell-shaped, use the empirical rule, for example, then yeah, that's great. If you say it's not bell-shaped enough to use the empirical rule, I gotta do something else, good for you, that's fine too. There's a lot of gray in this class, a lot of gray. Back to what Jordan said about what relative position is for that matter. Okay, so we did a great job of describing this. Where's Max? See, that's the kicker. That's the kicker. I was given this after his checkup. I wasn't given an absolute value. I was given a relative value. The relative value I was given was he's in the 80th percentile for weight. And this is just, by the way, we're just looking at weights here, not his head girth and not his length. We'll get back to that too, that's fun. So, what I want to do is I want to ask a question. How many of the 2-year-olds in this sample weigh less than 26 pounds? How many weigh less than 26 pounds? You now know why I gave you that quiz question I did a couple weeks ago.
20.
Well, for more than just this reason.
20.
We gotta vote for 20. Well, here's 26, right? So let's figure out the ones that are below it. So we've got 8 here, plus 4, 12, plus 4 more is 16, plus 4 more is 20. Boom, boom, 20. So 20% are less than 26 pounds. Is that fair? This was that quiz question I gave you guys on the first quiz. What percent of these numbers are above whatever, blah, blah, blah. I had to go in there and kind of count. So getting you ready for this kind of analysis. So we're cool? 20% are less than 26 pounds. Good. Let's do it again just to make sure that makes sense. How about less than 29 pounds? How about less than 29 pounds? How many of them? Let me do it too. Did you get 49? You get 49? Roughly half of them. Roughly half of them. So 49%, or just about half of them, are less than 29 pounds. What does that mean about 29? We just found what? Call it 50%, just to make it easy. It's almost 50%. Not the average necessarily, but definitely if half are below it, we definitely just found the what? The median! We just found the median. It might be the average. That's why I said not necessarily. It could be the median. But we definitely just found excuse me, it could be the mean. We definitely just found the median, though.
Right.
And because essentially what you just did was but you chopped completely from one side. You looked at all the low values and you go to the halfway point. What we usually do when we were manually finding the median, we chop, and we end up in the middle by symmetric chopping. But you asymmetrically chopped and found it that way. Fair? So you just found the median, below which, so half of the data essentially, or half of the 2-year-old white American boys are less than 29 pounds. In this sample anyway. And earlier, what was it, 40% or 20% were less than 25 pounds. One more, because this is probably boring you at this point. What percent are less than 31 pounds? I'm doing this as a lazy guy, if it's okay with you guys. I counted up 31 and higher. Is that okay if I do that way? Yeah, you can do that too. It's pretty efficient. So if I gotta go less than 31, I'm like, holy crap, that means 30 and 29 and 28. You can just also just add these up and subtract it from 100. That'll give you the answer too. Well, you saw that trick in your first project. So the whole complementary idea. Look at the complement of what you're looking for. So that's 11 plus 8 is 19 plus 1 is 20, which means 80% of the sample is below 31 pounds. That's how I figured out how much Max weighed. Because I knew what essentially the average and the standard deviation were for 2-year-old American boys. As the reverse engineer from a percentile rank point of view, more of that momentarily. But based off of the sample, 80% of the data in the sample are less than 31, which means Max was heavier than 80% of the white American 2-year-old. That's the definition of percentile rank. Now, on your next take-home exam, I'll have you analyze some alternate related definitions of it. But this is the one I want to use. David, you nailed it. And Anthony, I think you nodded because you had heard that too. It looked like Jenny, you had heard it too as well. This is the one I'd like to use in class because it's the easiest one for us to process. Essentially, a percentile rank simply gives you the proportion that your data point you're talking about exceeds. That's it. Max was in the 80th percentile for 2-year-old white American male weight because he was heavier than 80% of 2-year-old white American males. Max was in the 90th percentile for white American male weight because he was longer than 90% of white American male 2-year-old boys. He's in the 85th percentile for white American 2-year-old male head girth because he's head girthier than 85% of white 2-year-old American males. The reason I bring this up, and the reason I like to look at it in context with this particular context, I guess, I used context twice and I apologize, is that, Jen, the reason I still have these numbers just to talk about it is because something very interesting happened at this checkup, and my wife was a total rock star. They took those measurements, they took his weight, took his length, took his head girth, and whoever was working with her that day pointed at the weight in the 80th percentile and said, what do you feed your son? And she said, food. And she knew where this was going. And they kept answering. So then Jen started listing out like the food that we ate. And then kept getting asked about this 80%. This 80% is very, very, very high. And then my wife shot back with, well, did you look at body composition? Did you look at the correlation between the fact that he's in the 90th percentile for length, 85th for head girth, and also 80th for weight? And she said the person probably started backpedaling and finally admitted that what happens is, my wife is so quick, I'm so proud of her. They said any weight that places a white American 2-year-old, and I'm assuming any young child, above the 50th percentile, parents are questioned for overfeeding, for overweight children. And any weight, this was verbalized to her, and I'm sure it was either heard wrong or said incorrectly. But any weight that came in over 50th percentile was questioned for overweight. Any weight under 50th percentile was questioned for underweight. My wife snaps back immediately. So basically, you're giving every parent a lecture that their kid is not the right weight. Because if you think about that, right?
There is no right.
Think about that. If you don't land at 50, you're getting a lecture. and then, of course, the poor person just gets sad and brain because you have the nightmare of a math person with their kid in there. But the point, I mean, it's well-intentioned, just poorly delivered. Like I think a lot of medicine is totally well-intentioned, but poorly delivered like that. I mean, yeah, they didn't even look at the fact that he was 90th percentile for length. I mean, yeah, he's 80th percentile for weight and he's 10th percentile for length. And we're like, well, let's talk about this. You can picture the kid.
They don't take into account genetics.
Well, even if they did, they don't take into account body composition.
Well, even if they look at his son, they'd be like, okay, he's fine.
He's fine, but they're looking strictly at a number. This happens so often in medicine, so often. I remember going in, did I tell you guys about the false positive I think I got for a thyroid test? Right, same thing. They look at a number in isolation as opposed to looking at everything else. And look at the rest of my blood work. Think about what I just told you. Do you think I'm hypothyroidic based on that one data point? It's probably not likely, but they're not trained statistically. So anyway, interestingly enough, this is probably an easier way. This is called an ogive, or a cumulative frequency histogram. I'm going to bump up to the ogive. This is usually what's used. But what you're looking at here is, remember when I asked you guys, I said what percent, or what number, how many boys are below 31 pounds, and you had to kind of go and add up. What's kind of cool about this is, if I ask that question, what number of boys in the sample are below 31 pounds, you go to 31 and go 1 over, and the height of that bar actually tells you. And the reason it works that way is, so for example, there were, I think, 3 boys that were 20 pounds in the sample. That bar is 3 high. I think there was 1 kid in the 21 bar sample. This bar is now 4 high because it's that 1 kid plus the 3 below him. So that's why I look at that at or below that weight. So at 21 or below 21, there were 4 kids in there. At or below 22, there's somewhere in the neighborhood of 7. At or below, at or below. So when I said how many weigh less than 31 pounds, that's at or below 30 pounds. So you go right over to 30, 80%. And notice this one tops out at, it has to, doesn't it? Because if the heaviest kid in the sample is 33 pounds, that means 100% of the kids in the sample have to be 33 pounds or less. This also ties into the exploration you guys will do on your next take-home exam, which is there's not one universal definition for the formula for a percentile rank. Depending on who you talk to, which textbook you read, which online reference you use, there's a problem. There's a problem with just looking at a simple proportion. You can never be in the 100th percentile. Technically, you can't, can you? Because even if you're, suppose we take all 2-year-old American males, all of them. In that entire data set, there's one that's the head girthiest. Has to be, right? He's got to be the head girthiest. He's the biggest head in the sample, or in the population even. He can't be the 100th percentile, because the definition of percentile is a percent of those that you are bigger than. You can't be bigger than yourself. So in other words, he's the 99.99999th percentile or something along those lines. Does that make sense? Another catch is there's also a kid down this end with a head this big. That's the smallest. What percentile is he? He actually is the 0th, isn't he? He can be the 0th percentile. By how we've chosen to define it. We've defined it by the percentage of those you exceed. that kid down there exceeds nobody. So 0 over whatever is 0. So that upsets people. So what they do is sometimes they alter the formula so that there can't be a 0th percentile, like whatever. So I'll have you guys analyze this on your take-home exam next time around. Because it's worth talking about, because you have to kind of know what formula is being used when you're talking about data, especially when it comes to things like the TEAS exam, when that result is actually deciding whether or not you get into a program. You want to know how they're calculating it, and if it's advantageous or not for you. So, regardless, I want to stick with this context right now, though. This is just a graphical form of that called an ogive. I like the word, don't memorize it. I like the word only because it's so much different than everything else in statistics. Histogram, relative frequency histogram, cumulative relative frequency histogram, cumulative frequency ogive. It's a great, like, goofy word name. But here's the one. This is the one they show you when you take your kid to the pediatrician. Now this is a 0 through I think 3 years. This is 0 through 3 years growth chart. And it's uber complex to look at. It's kind of nausea-inducing at first because there's so much going on, but it's actually pretty straightforward. I mean, you just go, you figure out where he is. So he was 2, so there's 24 months. You got weight and length on the same axis. So basically what you do is you just go 24. Now, we knew he was 31 pounds. That's what he was measured in at. So you got pounds. So you go to 31, and then you come up here, and you go across, this is 31 right here, until you intersect, which is roughly right there. Now take a look. There's the 75th percentile. There's the 90th percentile. So you just call that the 8th percentile, which is probably not exactly accurate. It's accurate enough. He's heavier than 4 out of 5 kids, which, you watch the kid. Yeah, I mean, he's a big kid. Now, there's also, if you notice, when they're very young, the 5th to 95th percentiles are very close together. And as they get older, they spread out very, very, very much more. This is why when decisions are made at very young ages about kids and their percentile ranks, I get very nervous. A quarter pound can make a huge difference in percentile rank at birth or at 3 months or at 6 months. And that quarter pound might be an error in how the baby was measured. I mean, they strip them naked and put them on the scale. Totally correct. If that baby pees while on the scale, the liquid could actually weigh enough to I mean, honestly, there's all kinds of little goofy things like that. If you weigh that child at 3 months old incorrectly, and you put them in the 75th or 8th percentile when it should be the 30th percentile, which is not that big of, I mean, it's not that much of a difference if you pick any given, like three months here. It isn't that much of a pound difference from the 25th to the 50th. So the measurement precision is really, really important. It gets way less important as they get older, because body types start kicking in and things change, just as a function of how we are.
It's important because they made their own decisions, unfortunately.
They can. It's potential. Hey, Jules. It's potential. It's potentially damaging if they make the wrong decisions. But that's the thing. When they tell me Max is in the 80th percentile or 85th for head girth, which is my favorite, then I have to say, okay, that's cool, but are we upset about that? Why are we upset about it? Go ahead, Anthony. Yeah.
So do you use it as a predictive then too? Do you follow the line up until down the years?
That's a great question. Anthony asked, can you follow, like, so at 5 and 6 and 7 years, and kind of say, you can if you know how the line is behaving. Because if you take a look at this, it's actually tied back to the bell curve that we'll study in a lot more detail later on. But you can't just, it appears to linear out here a little bit. It doesn't linear out. There's actually some behavior there. I'm going to have you guys later on look at the 0 to 5 and 6 year line, because that's where Max is headed next. The trick is, because of all the inherent variation in these tight quarters here, the weights and heights and girths tend to regress back to the mean after a while. So Max is now in like the 60th percentile, 55th percentile, so he looks more like a typical, if you were to call it a typical 2-year-old kid or a 5.5-year-old kid now. Please, Liz.
I'm just curious, is that how doctors might be able to assess what a child will end up growing into, what their total height is?
It's one tool. There's another one that they've often used called mid-parental height. I love this one, and I don't know what the margin of error is on this one. So this is a fun one. Take your mom's height. Everybody try this right now. Well, you might not know it. You don't know it. Take your mom's height, your dad's height. Add them together. Well, average them. Average your mom and your dad. And add 2.5 inches. That should be roughly what your height is. I've been given that one. So if you know how tall your mom and dad are, average that, add 2.5 inches, and that's roughly what your ending height should be. It seems far too neat to me, but that one is actually used. So yes, this is a tool, that's a tool, there are other tools as well. And that's one of the things I said when they talk about Max's 80th percentile. What about body composition? Sure, he's 80 pounds, but 80 pounds of what? Is he bone? Is he 80 pounds of muscle? Is he 80 pounds of fat? Totally different situations. So yes, one of many tools, and I think the more tools you use, the better, because the more tools you'll use, you'll get a modal result, and you can see if that 80 is just an outlier data point. Anybody close to what their midparental height is?
How do you do that?
Just average your mom and dad's heights together. You exactly, Jade, it's exactly. So whatever your mom and dad are, average their heights together, and add 2.5 inches, and that's what you quote unquote should be, how tall you should be. Yeah. So my dad's I think my dad's like 5'10". My mom's like 5'7". So that averages to 5'8.5". And if I add 2.5 inches to that, that comes out to be 5'11", which is I'm a little bit taller than that, but I'm roughly 5'11". So ish. Am I getting close to what that predicts? Close-ish. Within an inch or two? Yeah, within an inch. Within 5 inches?